Next, we are going to deal with the Thevenin's theorem. This theorem you are going to see virtually everywhere in networks, not only in networks but in other subjects as well. So pay attention to this. Okay. So first write down the statement. A linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with resistor RTH. Okay, so TH is nothing but a short form of for Thevenin. Okay, so now what is VTH here? What is the value of VTH? VTH is going to be the open circuit voltage at the terminals. Once we do a problem, it will become more clear to you. Okay, so for now, just write down the terms. Open circuit voltage at the terminals, it is called as the Thevenin voltage, and RTH is the equivalent resistance at the terminals when independent sources are turned off. All of the independent sources, okay, are turned off. What will happen to dependent sources? They should not be turned off. Okay, so do not turn off dependent sources. So linear, we anyways know what is a linear circuit. It is a circuit which contains only linear elements. Okay, and an element is called linear if the VI relationship is remaining as linear. Okay, a two-terminal circuit, that means you can just consider some circuit here. Okay, and it has two leads outside, two terminals you can take outside. Okay, so that is nothing but a two-terminal network. If you take out three terminals, then it is going to be a three-terminal network. Okay, so now this can be replaced by a voltage source whose value is VTH, which is in series with a resistance RTH. Okay, so that means if terminals are A and B here, then this will also be A and B. Okay, so this is the statement of the Thevenin's theorem. We will take an example here. Obtain Thevenin's equivalent of the circuit. So this is the circuit and the terminals here is A and B. So that means you can consider that this here is the two-terminal network which has to be replaced with its Thevenin's equivalent. Okay, so we will see how to do this. The first step is to find out VTH. Finding VTH. In order to find VTH, what you have to do? You just have to find out the open circuit voltage at the terminal. Okay, so it is basically the same circuit only. 32 volt, 4 ohms. Here you have 12 ohms, and here you have 2 amperes. This is the current source, and this resistor is 1 ohm. And now we have to find out the open circuit voltage VTH. Okay, now how to find VTH? Here you can see that this is 2 amperes. Now here you can see that this voltage source is in series with a resistance. So you can apply source transformation and you can get a current source in parallel with a resistor. Okay, so now this one resistor you will get parallel. Here you have a parallel resistance. You can easily find out equivalent resistance, and 2 current sources in parallel also you can very easily find out the equivalent current source. Okay, so applying source transformation, you're going to get a current source. What will be the value of this current source? The voltage source divided by 4. 32 divided by 4, which is equal to 8 amperes. And here you're going to get 4 ohms, 12 ohms, and the 2 ampere current source. This is VTH. Okay. Now 4 ohm and 12 ohm in parallel, you're going to get 3 ohms. And what about the current source? 8 plus 2, 10 amperes. And this is 3 ohm. And this here is 1 ohm. Okay. Now once again you can apply source transformation. You have a current source in parallel with a resistor. Okay. So then what are you going to get here? Again applying source transformation, you're going to get a voltage source whose value is 10 into 3, which is 30 volt, which is in series with 3 ohm and a 1 ohm resistor. Now it is very simple. It is open circuit, no current is flowing. Then VTH is simply equal to this voltage source. So VTH, therefore VTH is equal to 30 volt. Next what we have to find? We have to find out the Thevenin resistance. Find the Thevenin resistance RTH. This was the original circuit. Now you have to replace the independent sources with their internal resistance. So this is, since nothing is given, we can consider it to be ideal sources. So this should be shorted and this should be open circuited. Okay, so that's how you turn off, right? So you're going to get the circuit like this. Here you have 4 ohm, here you have 12 ohm, and this is open circuit, and here you have 1 ohm. Okay. Now looking through these terminals, you have to find out the equivalent resistance. So you can see here that you have 1 ohm which is in series with this combination, and this combination is 4 ohms in parallel to 12 ohms. So what are you going to get here? RTH is equal to 1 plus 4 ohms parallel to 12 ohms. 4 ohms parallel to 12 is, we have found previously, 3 ohms. So 3 plus 1, you're going to get 4 ohms. Okay. So what is the Thevenin's equivalent? The final Thevenin's, therefore the final Thevenin's equivalent is a 30 volt source in series with a 4 ohm resistor. Okay. Now what is the significance of this equivalent source? Why do we need this equivalent source? So let us say we connect a resistor here. Okay. RL, let us say. Okay. Now we want the voltage across it, VL, and we want the current across it. Okay. Now imagine yourself working through with this entire circuit, and imagine working with this circuit. Once you simplify, then whatever resistance you have here, whatever the value of this resistance, it will be simpler because now you have a simple circuit. Okay. So let us say you have the resistance RL connected here. So this will become VL and this will become the load current IL. So what will be the value of VL here in the second circuit? You can apply the voltage division rule. The resistance RL divided by the sum of resistors into the total voltage. And IL is simply going to be 30 divided by 4 plus RL. Okay. So whatever the value of RL, you now have simple expressions to find out the voltage and current through this resistor. Imagine working on this. For different values of RL, you will have to work all over again, right? So that is the significance of the Thevenin's equivalent circuit. Now we are going to do one more question, but here you have a dependent source. So how will you work when there is a dependent source? Okay. So the first step is to find the Thevenin's voltage source. So this is going to be as it is. There's not going to be any difference just because there is a dependent source. Okay. So we will draw the circuit again. This is 5 ohms and here you have the dependent source 1.5 Ix, 3 ohm resistor and the 4 ohm resistor. The current Ix is flowing here. Okay. Now this is A and B terminals. Here you need VTH. Now here you can apply source transformation. Okay. So applying source transformation to what? What are we applying the source transformation for? for this voltage source in series with this resistance, because then you will get a current source which will be in parallel with another current source. Okay, but remember, you cannot transform this element because it is having the controlling variable Ix. Okay, so we are going to get here the current source is going to be 6 by 5, and this is the 5 ohm resistor, and this is the current source 1.5 Ix, and here you have as it is. Okay, so this is VTH. Now these two current sources you can add, right? So here you're going to get a resultant dependent source, because 6 by 5 plus 1.5 Ix, right? And here you have the 5 ohm resistor and 3 ohm and 4 ohm, right? Now what is VTH? It is across this 4 ohm resistor. Okay. Now here you can apply the current division. So if you take the current here, we need the current here, so that VTH is going to be 4 times I. Okay. So now I you can find out by current division. Okay. And one more thing that you can see is, what is the current through 3 ohms? It is the current Ix. Okay. So this I is nothing but Ix. So by current division, by means of current division, Ix is equal to the total current 6 by 5 plus 1.5 Ix times, since there are only two resistors in parallel. Okay, you can either write reciprocal by sum of reciprocals, or because there are only two resistors, you can write the opposite side branch resistor divided by sum of resistors. Okay, so you're going to get 5 divided by 5 plus 7. Okay, now you have an equation in Ix. Okay, single equation and single variable. So here if you find Ix, you're going to get 1.33 amperes. Okay, now what is VTH? Therefore, the Thevenin's voltage VTH, which is equal to 4 times the current through the 4 ohm resistor, which is Ix. So you're going to get 5.32 volt. So we have found out the Thevenin's equivalent, and we don't need to worry much just because there is a dependent source. Now for the Thevenin resistance, you will have to consider some different methods. Okay, so to find Thevenin's resistance, you have actually two methods you have. Okay, so what is method 1? Whatever circuit you wish to convert into the Thevenin equivalent, that if you take as a two-terminal network. Okay, so this is A and B. Now if you connect a 1 ampere source here, okay, then this voltage, if you take as VAB, then what will be the Thevenin's resistance here? Basically Thevenin resistance is nothing but this entire network, there will be some equivalent resistance. So you can replace the network with the Thevenin's resistance, right? So this is A and this is B, and this is the 1 ampere source. This is VAB. And what is RTH? RTH is simply equal to the voltage across it divided by the current flowing through this. So this is nothing but the voltage, VAB. So if you connect a 1 ampere current source and find the voltage, that voltage is nothing but the Thevenin's resistor. But remember, you have to turn off all independent sources. Okay, so you can consider this like first step, turn off all independent sources. Now connect 1 ampere source at AB terminals, and now find VAB. Okay, and you're going to get RTH is equal to VAB by 1. Okay, this is method 1. Similarly, you can connect a 1 volt voltage source. So method 2 is going to be just almost similar, only just instead of current source you're going to have a voltage source. So that means this is the network. Here you have 1 volt. Now this current, let us say we will take it as IAB. This is AB and AB terminals. Okay. So what is RTH now? This is the resistance with which we can replace the network. So this is 1 volt. This is IAB. Now what will be RTH? RTH is equal to 1 volt, the voltage across it, divided by the current through it, which is IAB. Okay. So here what is the procedure? The first step is same as in method 1. The second step is connect 1 volt source at AB terminals. Okay. And you have to find IAB, and from there you can get RTH is equal to 1 by IAB. Okay. So because it is a little more simpler to just simply find VAB. VAB will simply be the Thevenin resistance. I tend to follow the method 1, but you can follow whichever is more convenient for you. So now we will find out the Thevenin's resistance for our particular example, right? So here we have 1 dependent source and 1 independent source. You have to first turn off the independent source. So we are finding RTH using method 1. Okay. So what is the first step? You have to turn off all the independent sources. So you're going to replace the 6 volt with a short circuit. This is 5 ohms. This current is 1.5 Ix, 3 ohms, 4 ohms. Okay. Now what is the second step? You have to connect a 1 ampere source here. Okay. So this you can say the first and second step. 1 ampere source. Now we need to find out the voltage VAB. Now the third step is to find out VAB. Okay. Now what was this? The current through 3 ohms is Ix, right? So if you apply KCL at this node, 1.5x is flowing here, Ix is flowing here. So here the current should be 0.5x in this direction. Okay, 0.5 Ix. Now at this node, you have 1 ampere flowing like this, Ix is flowing like this, then what will be the current through 4 ohms? This is going to be 1 plus Ix. Okay. Now what you can do, you can apply the KVL in this direction for this super mesh. Okay. So you can write the voltage drop across this is positive only, 4 times 1 plus Ix. But through this it is going to be negative because we are going in this direction and the current is in the opposite direction. So you're going to get minus 5 times 0.5 Ix, and to 3 ohms it is positive. So this is equal to 0. So now you have one equation in one variable. Ix, if you find out, you're going to get minus 40 by 45. Okay. Then what is the value of voltage VAB? This is going to be 4 times. See, this VAB is nothing but the voltage across this 4 ohm. Okay. So 4 times 1 plus Ix. Ix you know. Finally, VAB you're going to get as 0.44 volt. Okay. So from here, RTH is equal to simply VAB, which is 0.44 ohms. So this is how you find out the Thevenin's equivalent when there is a dependent source. One point that I wish to tell here is when there is a dependent source. When there is a dependent source, then the Thevenin's resistance can sometimes be negative. Not all the time, but it can sometimes be negative. Okay. Maybe negative. So even if you get a negative answer, do not panic if there is a dependent source. If there is no dependent source, then you should get positive only. Resistance will be positive. Okay.